Section 1.2 is titled Constructing Models to Solve Problems. This is a problem-solving section. Oftentimes when you teach math, students will ask things like, when am I going to use this in real life? Have you ever said that? My sixth graders keep saying that right now. They're not real excited about working with fractions at the moment. So the catch is that then when your professors or your teachers or whatever want to show you things that you use in real life, oftentimes students don't like that any better. This is one of those sections. This is some real life stuff. So they're real problems. Maybe they're not real life to your specific life, but these are ways in which mathematics is used in application problems. Now, there is a list of equations. I'm going to slip over here to this for just a moment. It says some common formulas. I'll come back to the slide before in just a second, so don't fret for the moment. But there are some common formulas, and these ones right here, some of them you probably know. If I asked you what the area of a rectangle is, I bet you would know that that's length times width, right? Probably know that one. If I asked you how to switch between Celsius and Fahrenheit, maybe not. It's not something we do all the time. But these formulas right here, this is the one and only time during college algebra where I will give you formulas to use on a test. These are the ones I'll give you. They'll actually be listed out. So I'm not asking you to memorize these 7 formulas, even though you probably know a couple of them already. But you better know how to use them, because it's not going to say, go find the distance formula. Use it to da-da-da-da. It's not going to say that. It's going to be a real problem that's going to ask you the question and assume that you can go and figure out which formula matters and makes sense for the context that's being used. Okay? Now, let me go back to the slide before, but just so you know, these are the ones that are actually going to be given to you. You really don't need to copy them down, or if you want to copy them down, you'll have to later, because they're inside of Canvas in 2 different places. So let me come back over here first. Models. Models are how we would take real life and turn it into a mathematical way to solve something. So a formula, specifically, is simply an equation involving 2 or more variables. A function is a rule for determining the value of one variable from the value of one or more other variables. And of course, you've seen my next slide where there are 7 different formulas. So again, if you're not quite getting everything written down, please just print the notes or reference this later and fill those details in, because I do want to make sure we finish. Yep, they're on Canvas, both in the PowerPoint view and in this handout view, which is a little bit more pretty. It's prettier. So these are some common formulas. Simple interest. You've probably used that one before. Maybe not recently, but that's how interest is calculated when it's simple interest. Perimeter of rectangle, you add up all of the lengths and widths, right, all the way around the rectangle, so it's 2 times the length plus 2 times the width. Distance is found by multiplying the rate at which you are running, biking, driving, and you multiply it by the time at which you're doing that, how long you're doing it for. Temperature, Celsius is 5/9, Fahrenheit minus 32 degrees. Sales tax, whether you realize it or not, again, you do this every single time you shop, right? They take your total and then they add on a tax amount. The tax amount is found by taking the tax rate times the amount of your ticket, and then they add that to the original amount of your ticket. At the bottom, it tells you your total amount that you owe the grocery store, the convenience store, Chili's, whatever. Area of a rectangle is length times width. And then work is actually rate times time. You'll notice that that looks a lot like distance. It's a different kind of context, but it's actually found the same way. So these are the ones that we're going to actually use in this section contextually to do things. Before we actually do that, I want to talk to you about how we solve formulas that were given. And so the formulas in the examples 1, 2, and 3 are not necessarily anything of these. They're just some other formulas. They're probably ones you recognize. But my goal is that I want you to learn or to remember how you solve for a variable. And we've talked about this in intermediate algebra, but they're going to become a little bit more challenging perhaps with some of the formulas they give you. So on the first one, on A, area equals 1/2 base times height. Anyone know what that is? It is the area of a triangle. Yeah, it doesn't ask you that, but I was just curious if you knew. So our goal here is to solve for B. So we want the B value to stay where it is and everything else to move. Now, while we could divide by 1/2, division by fractions looks kind of messy, and we've learned other ways to deal with that. Instead of dividing by 1/2, we can multiply by the reciprocal. So the reciprocal is 2/1 or just 2. So the first thing I have is that 2a is equal to bh. And then what would I do to get b alone? I would divide by h. So b is equal to 2a over h. Okay? We're not giving any numbers. We're not plugging anything into anything. We're just shifting all of the constant values around, or the variable values around, and solving for one of them that remains.
So when you do the reciprocal on the 1/2, it cancels out?
It does, yes. So 2's cancel, I'm left with 1.
So you just divided h from bh?
Yes. So the h's cancel as well.
So then, well, no, never mind, I understand now.
Okay. All right, any other questions on that one? Okay. Next one looks a little different. I have ax plus by equals c. This is actually an equation for a line. It's not the standard one we normally see. It actually is called the standard formula for a line, though, by the way. So on this one, we're supposed to be solving for x. So if you're sort of thinking about working from the outside in, the piece that's furthest away from x but still on the same side of the equal sign is the by, right? And it's currently added, so we will compensate by subtracting. So we will subtract the by from both sides. So I have ax on the left, and I have c minus by on the right.
Divide by a?
Yep. And then our next step would be to divide by a. So x is equal, and it's not pretty, but it's correct, and there's no simplification we can do, c minus by over a. Okay, so 3 is ugly. Y'all ready for 3?
No, hold on.
Okay. Sorry, I have a headache, guys. All right. This one looks really funny because the letters look like they're matching, but they're not exactly the same. Have 1 over r equals 1 over r1 plus 1 over r2 plus 1 over r3. Okay, all of those r's are different variables. They could just as easily say a, b, c, d. They just don't. Okay? All right, so specifically it wants us to solve for several things we could do to solve for R2. Went off on me? Okay, let me see here. Okay, we're back. So if we're thinking about it kind of like we did this last problem where we're sort of working from the outside in, what's furthest away from R2, the pieces that we might want to move first are these two. Does that make sense? And they're added, so I'll just subtract them over. The bad thing is it means that there's fractions still in the problem, but the reality is there's going to be fractions somewhere along the way anyway. We're not going to be able to eliminate them. It's not solving the way we've been doing before, so we're going to have to deal with them somewhere. So the first thing I'm going to do is I'm going to subtract 1 minus r1 and subtract 1 over r1, and then subtract the 1 over r3. And we do it to both sides. So on the left-hand side, I have 1 over r minus 1 over r1 minus 1 over r3. And it equals 1 over r2. So I mean, like, it would be awesome if we could just take two sides and just flip them, right? Like fractions, right? We could just flip fractions upside down. The problem is that the left-hand side doesn't have one fraction, it has 3 separate fractions. And I can't just flip all 3 of them. That's not appropriate, it's not correct. It does not equal the same thing. I can't just flip fractions upside down unless I have a single fraction on each side. So I do want to flip them upside down, which means I need to have a single fraction on the left-hand side. Okay? So they don't match R1, and R3, but they are going to be the common denominator, R1, and R3. Okay? So what I need is I need my denominator to be R1, R3. That's going to be the denominator that has all 3 pieces in it, which means my first fraction needs to be multiplied by R1, R3 on top and bottom, not B, R3. The second one needs to be multiplied by R and R3 on the top and bottom. And the third one needs to be multiplied by R and R1 on the top and bottom. The other side of my equation does not get affected. There's no reason to mess with it at all. So what we would notice, there's no canceling here either, and all my numerators are 1s, which is actually, that part's friendly. So when I multiply R1, R3, and 1, I just get R1, R3. And there's a subtraction sign, but then I multiply 1 and R3, and I get R and R3. And there's a subtraction sign, and then I multiply 1 and R1, and I get R and R1. So again, I realize it doesn't look pretty, but it's almost like you're doing Sudoku or something like that. We're sort of solving a puzzle. And the reason that we did that again is because if I have both sides of the equations in one fraction, I can flip them both upside down. So on the left-hand side, I can make this a little smaller for the moment. R1, R3 in the numerator now, over R1, R3 minus R3 minus R1. And it will equal, and if I flip this upside down, I get R2 over 1, or just R2.
Did you flip the fraction upside down?
We did.
Okay.
So we flip the top here and bottom, and flip the top and the bottom here as well.
Is it always going to be like letters like this? Or is this
No.
just like-
There's just going to be a few that you're going to do like that. We're about to get into the ones that have got actual word problem stuff. So you're not going to do a whole ton of these, but you're going to do a few where you're manipulating symbols. That's what you're doing, is manipulating symbols. Okay, that one's a long one. That's it. We're done. I told you it's not pretty, but we're done.
So the final answer is 1 over R2?
No, the final answer is in the box. The final answer is R1, R3 divided by R1, R3 minus R3 minus R1, and that equals R2. So it would probably have you write all of this into my math lab, would be my guess. There's a subscript button. That's what it would do. It would definitely have a subscript button available at that point, if you had this particular problem. Okay. Are you ready to shift gears? Okay, so this was mathematical manipulation. We're going to be doing some of this as we work through our problems, but they won't be as ugly when we have actual data. So what we're going to be doing is we're going to be doing problem solving. This is a 7-point problem-solving strategy. I am not asking you to write down, here's step 1, look at my work. Here's step 2, look at my work. This is meant to be sort of a guide so that you have sort of sitting next to you and you say, okay, what was it I was supposed to do next? Oh, that's right. I need to make sure about this. Or, oh, that's right. I need to double check on that. Or I need to make sure that this answer, whatever step you're on. Okay? So the first thing we should do anytime we're dealing with a problem is to make sure that we read and understand what the question's asking. I know that seems sort of obvious, but sometimes I'm telling you what, I see students just move right on through the question. I'm like, what did it ask you to do? And they're like, oh, it said multiply. And what'd you do? I added. Okay, well, let's read the words. We've got to make sure we're actually doing what it asks. So be careful about that. The second one is to draw a diagram if needed. Sometimes diagrams are helpful. Depends on what we're doing the problem about. If you're talking about something where it's an area of a rectangle, it might be helpful to draw an area, and a rectangle to talk about the area. It also depends on your learning style, right? Are you a visual learner? Does it help you to see diagrams? I personally am, so I draw a lot of diagrams. My diagrams are terrible because I don't draw well, but it gives me sort of a visual to fall back on. The third thing, okay, so 3 is kind of a non-negotiable. You need to decide on a variable and write unknown quantities in terms of the variable. Okay, do you want to use X for the length? Do you want to use L for the length? You got to decide. It doesn't really matter. You just need to decide. Step 4, you need to write an equation using the formulas and or problem specifics. So you're going to have to figure out what is it asking, which equation matches the description of what I'm doing. 5 is to solve the equation. And then 6 is to check the solution in the equation and in the problem's context, right? So if the question asked you, how many children are born in the year 1992? It's not going to ask you that, but I'm just making it up. And you say 42.7, we have a problem. Right? Okay, it's got to make sense in the context of the problem. So what would you do in that case? Well, you'd have to round somehow. I don't know if you're going to round up or round down. It might depend on the context as well. But there are cases where you might actually take an actual legit answer and round it somewhere. Or there may be cases where you're like, okay, I got a decimal and that is not what I was supposed to be getting and I shouldn't have got a decimal. There's no way I should have got a decimal in this problem. So now you know you made an error somewhere to go back and fix. And then number 7 says to make sure you're actually answering the question that's being asked. Okay? So to give you kind of an example of that, I have a different class and we talked about a simple interest example the other day. They had one on their test. And their question on their test, this is actually an elementary ed class where they're going to go teach, elementary and middle grade students. And so their question actually asked them to create a question that asked the student to find the simple interest in a situation. That's what it asked them to do. So Sally went and she borrowed $1,000 from her mom and dad for her first beater car, and they're charging her this much interest. How much interest will she be, having to pay them back if she pays them back over the next 2 years, right? That's what they're supposed to be creating. But they actually had to have a question that said, find the interest, like that was the whole problem. And then on the next part of the problem, I had them actually solve the problem they created. Well, sometimes they solved the problem, but they didn't actually answer the question that they had from part A. Right? They answered how much Sally was going to pay in total for the car. She's going to pay $1,200 for the car. Okay, great, but how much in interest is she going to pay? That was what I asked you to find, right? So be really careful at the end of the problem that you're actually answering the question that you're asked to find. Just because you found x equals 7 doesn't mean that that was exactly the question you were asked to find. It may be an intermediate step and there's just a tiny little bit more you needed to do. Okay? So let's take a look at some problems. We actually are starting with one that is interest. This says if you borrow $100 and pay back $105 at the end of 1 month, what was the simple annual interest rate? All right, so if you flip back over to the formulas on the front page, simple interest formula says that you have, I equals PRT. Do you see that? Okay, we didn't talk about any of these letters are, so let's see if you remember. What do you suppose I equals?
Interest.
The interest, and that's like the dollar amount of the interest, okay? What does P equal?
Percent.
Nope, but good guess.
Oh, for sure.
Do you guys remember? It's called principal, and that's not the guy at the school, the principal or the woman. That's not what we're talking about, right? Principal. Principal means the amount of money that you either put into the account, like if you're saving money, or that you borrowed from somebody if you're borrowing. Okay, that's what principal is. R is an interest rate, so that's where that rate comes in. It needs to be expressed as a decimal of the percentage, right? So let me actually write that one down because that's an important feature here on this one. If you have R is 0.02, that would be 2%, right? The decimal has to move for a percentage 2 places. The other thing that's really important is that the T is time in years. So on this problem, for example, they tell us a number of months. How much is 1 month of a year? It's 1/12, right? So in our problem over here where they actually gave us a number of months, our T needs to be converted into a number of years. So let's actually start there. So T is 1/12 because 1 month is 1/12 of a year. Okay, the interest rate's what I don't know. That's actually what the question asked, right? So the interest rate, I don't know. That's the R here. So I'm going to leave that as the variable. I do know my principal. What was the principal? $100. It's what I borrowed. And the interest is actually the amount of money extra that I had to pay for the luxury of borrowing. That would be my 5. Okay, so the interest is not 105. I did not pay 105 after I borrowed the 100. I paid the 100 and I paid 5 extra. 5 is the amount of the interest. Okay, does that make sense? Okay, so you'll notice that this 100 and this 1/12 are both being multiplied by R, right? So they're also being multiplied by one another. Now, go ahead and multiply them by one another. Well, let's just write it as 100 over 12 for now. Actually, I think that might be easier, and we'll do the multiplication in a moment. So 100 is being multiplied, the 12 is the denominator, so kind of like division. And then we can multiply by the reciprocal like we did a moment ago. So 12 over 100 on both sides. Okay, so the 12s, of course, cancel, the 100s cancel, leaving me with the R on the right-hand side, which was the whole point. Okay, so this is 5 over 1. If you'd like to reduce first before you do the division, that's fine. If you just want to multiply across the top, multiply across the bottom and divide, that's fine. What do you get when you do this multiplication? What is it? 60 over 100, okay. So what is 60 over 100? What is R? What was it? Okay, so we want to do this in decimals. I know we've done a lot of stuff with fractions, so your mind's probably thinking about that. We want this in decimals because we're talking about a rate, which is like a percentage, right? We're going to turn it to percent in a moment. What is it as a decimal? 0.6. Okay, so right, your calculator will do 60 divided by 100. Okay, 6.6. What is 0.6 as a percentage? Because an annual interest rate is a percentage. It is 60%. It's tempting to think it's 6, but every time you have to multiply by 100, moves the decimal twice, right? 60% is my interest rate. That's huge, by the way.
That's freaking giant.
Absolutely enormous, huge. But it's only $5.
Yeah, but that'll get bigger over time.
So, yeah, over time it would not be a good thing to do for sure. Okay, does that make sense? Okay? All the pieces, they filter into all the places. We're simplifying. We're working with decimals because the context makes sense that we need a decimal so that we can turn it into a percentage. That's the context. Damaris.
So when I initially looked at the problem, I thought it would be 5% because $5 is 5% of $100.
Mm-hmm.
So why does that not work?
Because it would be 5% if the interest rate were for a whole year, if this was over the term of a year, if she paid $5 for a year, but she's paying $5 for a month. So what you're actually taking is that 5% and multiplying it by 12.
So could you do it?
That's
that
what
way?
gave you 60%. You could, as long as you set everything up properly, you could. I feel like that's a very specific question related to this particular type of a context, and it's not always going to say 1/12 of a year, right? Or something like that. So it might not work sort of as a generalized process. Okay, let's take a look at the second one. It's a temperature one. If the temperature at 11 p.m. on New Year's Eve in Times Square was 23 degrees Fahrenheit, what was the temperature in degrees Celsius? Okay. Well, the good news is you have an equation given to you, right? All right. We have Celsius equals 5/9 Fahrenheit minus 32 degrees. Okay, that's the equation that was given back on that first slide, or second slide, or whatever it was, your first page. Okay, the nice thing on this one is that they only have one quantity that they gave you, and there's only one place that it makes sense to put it. Where's the 23 going? It's going where the F is. So we have 5/9 equals 23 minus 32. This one actually simplifies really beautifully. That doesn't always happen. But what's 23 minus 32? Awesome. All right, 23 minus 32. What's that?
That is a good question.
It is a good question. It is -9. Like I said, that's actually a really nice one because it's going to cancel with the 9s in the denominator. That doesn't always happen. If it didn't happen, of course, your calculator could assist you, but this is going to give me on this one, very friendly enough, -5. -5 what?
Degrees Celsius.
Thank you. Degrees Celsius. Make sure you use units.
Where should we get the -5 from?
Well, there's a negative right here, and there's a 5 right here.
Oh.
Yep, just combining them. No problem.
How did 5 turn negative if you were just canceling out the 9?
Because the 9 on the inside's negative. Yeah, there's a 9 right here, or negative right here inside with the 9. So it cancels really to -1, not 1. Yep. Okay. All good? Okay, 3 is much more interesting. Let's take a look. I'm definitely going to need more space than this screen's going to allow. I'll have to flip to another screen.
Although,
You want to be farmer?
no.
Maybe someday you'll plant a garden, though.
Imagine. No.
Do any of you have gardening aspirations? Does anybody want to own chickens? It's a very popular thing to do these days, own your own chickens. I have no intention of owning my own chickens. All right, let's talk about Julia's soybean field. All right, her soybean field is 3 meters longer than it is wide. To increase her production, she plans to increase both the length and width by 2 meters. If the new field is 46 meters squared larger than the old field, then what are the dimensions of the old field? Okay, so this is one of those ones where I'm like, I need a picture because there was a lot that just changed in her description of what she's doing with her field. So draw a rectangle. She has a rectangular field to start with. And I'm not drawing anything in terms of like to scale. There's nothing about that going on. It says the field that she has is actually 3 meters longer than it is wide. So I like to use variables usually that represent the letter I'm finding when it makes sense to do so. So I like to use the letter W here for width. If you want to use X or something else, you can. Don't confuse yourself and use L. That will be really confusing later on, right? But W is good. And it tells you that the length is actually 3 meters longer. So right now, one length of the field, one side of the field is W, and the other side is W plus 3. 3 longer than the first side. Okay, does that make sense? Okay. What Julia's decided to do is she's going to increase the length and the width of her field. She's going to increase each of them by 2 meters. So no longer is her width, actually let me put this on the inside just so I have more space to draw. No longer is her field going to be W plus 3 times W, right? It's going to be 2 meters longer in each direction. So These lines should, of course, match up. They're not matching up perfectly because I want to make sure you can still see both of my fields. Okay, they're supposed to be right on top of each other. So this field is now, this is 2 right here. So the whole length here is W plus 2. Does that make sense? It was W, now it's W plus 2. Now this piece, we said before, was W plus 3. So we now have W plus 5. Okay, so it was W and W plus 3. Now it's W plus 2 and W plus 5. Okay? The other thing that it says is that the overall increase in production area is 46 square meters. So it's talking about this space right here. That space right there is 46 meters squared. Okay, everybody okay so far? Okay, so I have 2 different fields. My fields have 2 different areas, and the difference between those areas is 46. The big field is 46 smaller than the little field. Okay, so far so good? Okay, so I'm going to write down some of those details on my next slide. I think, let me try this.
Can you go back to the other one real quick? Oh, never mind.
I'm going to put it up here as a reference point. Oh, it's a little bit cut off, isn't it? Because my screen's too big. Because I can't project the way I want to, but that'll work. I think we're okay. Okay, so let's talk about our 2 fields. We have the old field, or how about I call it the original field? And then I have my new field. The original field had a length and width of W and W plus 3. The new field is W plus 2 and W plus 5. Agree? And what I've done, if I've multiplied them together the way that I've written them, is that I've calculated each of their areas. So this is sort of area number 1, and this new field is area number 2. Those are the areas of the individual fields. Okay, so area 2 is the bigger area, right? So if I were to take area 2 and I were to subtract off area 1, I would end up with the 46 square meters in the shaded area. Or you could say, another way you could think about it is if I were to take area 1, the little area, and I were to add 46, I would end up with area 2. If that one makes more sense to you. They're equivalent equations. Which one do you guys want to use? The first one or the second one?
The first one.
First one? Okay. All right, so this one's another option. We'll just set it aside for the moment. So the area 2 is W plus 2 times W plus 5. The area 1 is W times W plus 3. And this is supposed to equal 46. Okay, so we're going to do some algebra and we're going to distribute and simplify things out. So I'm going to multiply first and outer. So first is W squared. Outer is 5W. Inner is 2W. And then last, so inner plus 2W. Last is 10. So that's the first one I'll multiply it out. The second one, I'm going to distribute my W, and it's actually a negative here, right? So I have minus W squared and minus 3W. All right, combining like terms. What do you see? They do. Now, I'd like to make one more comment because I said it once before in section 1.1, and I'm going to say it now again here in 1.2. Yes, there was a quadratic at one point in time involved in this problem. But it has to eliminate or it would not be in this set of problems because everything I'm doing in sections 1.1 and 1.2 are linear equations. So in some way, shape, or form, it has to reduce down to a linear equation when I'm done. So if toward the end of the problem that w squared is not eliminating, there's an error somewhere. You've made a mistake. I should not have quadratics when I'm done with this problem to solve from. Okay? What else do we see?
5 plus 2
Awesome. So 5 plus 2 is,
7.
minus 3 is, okay, so that's 4w, and I have a 10. And this equals 46. So now what? Okay, subtract 10. So I need to save and move this up a little bit. Yep, so we'll subtract 10. All right, so what is 46 minus 10? 36. And if I divide by 4, what does that give me? W equals 9. Okay, be careful, right? One of our problem-solving steps at the very end said make sure the answer is what you're trying to find. I mean, I can put units on this all day, and it still may not be what I'm asked to find. The question over here actually asked me, what are the dimensions of the old field? So we have to plug W in. And the old field's the white one in the middle, the ones where I've labeled them in white. The dimensions are W and W plus 3. Well, W is 9. So what's W plus 3? Add 3 is 12, right? So W is 9, which makes W plus 3 12.
So 180?
It's not asking what's the area of the old field. It just asks for the dimensions. So dimensions mean, and is it in feet? Meters. 9 meters by 12 meters. Think about it like a picture frame or like the screen size on a television. They always tell you length by width kind of stuff. You all know what I'm talking about? Television's not a good example because they actually use diagonals on that. Pictures are good though, right? 8 by 10 picture frame, 4 by 6 picture frame, those kinds of things. So the dimensions means the length and the width. So this is a 9 by 12 meter field originally. Okay, any questions on that one? All right, let's go on to our next one. Brent lent his brother Bob some money at 8% simple interest. Then he lent his sister Betty, weren't those parents clever, half as much at twice the interest rate. Both loans were for 1 year. If Brent made a total of $24 in interest, then how much money did he lend to each one? Okay, so he's made 2 loans, right? Okay, so this is kind of like our last problem where we had the original field and the new field, and we had to create 2 different scenarios. That's how it's going to start. So we have our 2 loans. We have our loan to Bob. Good. And we have our loan to Betty. And we know we're working with simple interest, which is I equals PRT. Like that. So far, so good? Okay. So it actually tells us a little bit more. It tells us that his brother Bob had the money at 8% simple interest. So that's the percentage R right here. And if it's 8%, what is that as a decimal?
0.08.
Good, 0.08. And it also said over here, I think, that we were doing it for 1 year. Yes, both loans were for 1 year. So the loan time is 1 year. Okay, so far so good? It does not say how much money he gave them. Right? Not specifically, like it doesn't say $500 or anything like that. All right, so let's pause on that one for a moment. Let's go over to Betty. Again, doesn't say how much he lent her. But it does say for his sister Betty, he gave her half as much, let me slow down, half as much money. So if he gave Bob P money, he would give 1/2 P or P over 2, either way, to Betty, right? He gave her half as much money. But apparently Betty is not very trustworthy because he doubled her interest rate. So if Bob's interest rate is 8%, what's Betty's interest rate? 16%, which is 0.16, right? And the time is still for 1 year. Okay, so the first thing we're going to do is we're going to clean these up a little bit. If you have P times 0.08 times 1, that's just 0.08 P, right? Multiply by 1, yeah. If I have this 2 and this 0.16, I know it's not actually a 16, but what is 0.16 divided by 2? 0.08, right? It's the same value that happened to be on the other one. That's just coincidence, does not necessarily have to be that way for a problem like this with Bob and Betty and Brent. But I have P, I have the 0.08, and I have the 1, so I've got another 0.08 P here. It's just the way that it worked out. He could have said that he had doubled, that he had given her a third as much money. It could be P over 3. Or it could be that he tripled the interest rate and it could be a 3. There could be all sorts of different things. They don't have to work out this way. It just did. However, it does say that at the end of the year, Bob made 24 bucks, right? So this is how much money, whatever it is, that he got from Betty, and this is how much money, how much it is, he got from Bob. So he got 0.08 from Bob, 0.08 P, and he got 0.08 P from Betty, and it equals 24 bucks. That's what he made total. Because the question actually asks us how much did he lend to each person. So I do need to figure out what P is in this problem. So what is 0.08 P plus 0.08 P? 0.16, so 1600ths P. Then what would I do? We're going to divide both sides by 0.16. Your calculator will be a friend to you right now. So what is 24 divided by 0.16? 150. Now again, it is a dollar amount, but we need to make sure we're answering the question that was asked. It asked us, how much did he lend to each one? To each one?
Oh, no.
Okay, so let's do them one at a time. How much did he lend to Bob? Okay, so Bob, he lent 150. Because that's what P was. P was the amount that he lent to Bob. What about to Betty? Half that, which is 75. Half of 150 is 75. So he lent Betty $75. Okay. All right, let's do number 5. Rita can process a batch of insurance claims in 4 hours working alone. Eduardo can process a batch of insurance claims in 2 hours working alone. How long would it take them to process a batch of claims if they worked together? So, what you should know when you look at this problem is that it's going to be faster than 2 hours. Why? Okay, so in particular, it's because Eduardo can do it in 2 hours alone, right? So if he doesn't even have Rita's help, he'll be done in 2 hours. So if Rita were helping, it would shorten that time lower than 2. Does that make sense? So when we're thinking about our answer, it's really tempting on this one to say, oh, we'll just average them together. It'll take 3 hours. And we're like, wait a minute, that can't be right. Eduardo works faster than that all by himself. So it's not appropriate to just say that we need to average the values together or something like that. But whatever answer I get had better be smaller than 2, because Eduardo can do it in 2 hours. So what this is this is actually a work problem. So we've got Rita doing work, and we've got Eduardo doing work. And over on the front of your packet or whatever, work is equal to rate times time. Okay? So the time is what we're looking for. We don't know how long it's going to take each one of them. Agreed? Okay. But in a given amount of time, Rita works through a batch and it takes her 4 hours. So she works through one batch in every 4 hours. One is the batch on top, 4 hours is what it takes her. So T, if T were 4, she'd be done, right? With the full batch of insurance claims or insurance, whatever it said. Yeah, claims. Eduardo works through twice as fast, one batch every 2 hours. So if he were working for 2 hours, T equals 2 hours, he would finish his full batch of insurance claims. Does that make sense? So the fractions are telling you how much they can accomplish in 1 hour. In 1 hour, Rita can accomplish 1/4 of the batch of claims. In 1 hour, Eduardo can accomplish 1/2 of the batch of insurance claims. That's their rate. How much can they do in 1 hour? All right, so what they're going to do now is they're supposed to be working together. So this is how much they accomplish, each of them. So we're going to add them together. 1/4 T plus 1/2 T. And we want them to complete the whole job. Like 100%. Okay? What is 1/4 plus 1/2? It's 3/4. And if you weren't sure, because you and fractions don't like each other very much, remember we can get a common denominator, 2. So we get 3/4. Another thing you can do is you can think about it in terms of money. 1/4 and 2/4 is 3/4. So this is 3/4 T equals 1. And then what would we do to solve for T? What was it? Divide by 3/4 or multiply by the reciprocal. So I can multiply by the reciprocal. So 3/4 times 4/3 cancels, which is the reason we chose it. 4/3. 4/3 what? Of an hour. Now it feels funny to leave that way. If you told your boss it was going to take you 4/3 of an hour to finish, she'd probably look at you like, what are you talking about? I would too, because it doesn't make sense in that context, right? Like I'm as big a fan of fractions left like that as anybody, but it doesn't make sense for the context. So you can do one of two things. You can turn it into a mixed number, which would be 1 1/3 hour, which would totally make sense. If you told somebody 1 1/3 of an hour, that's okay. But you might also not like the fact that you're talking about 1/3 of an hour. Do you know how much 1/3 of an hour is? 60 divided by 3, which is 20 minutes. So you could also say, so this would be acceptable. Let me just say that. This would be acceptable. Or you could say it's 1 hour, 20 minutes. My math lab might make you do that. I don't know. But that would be another way of doing the problem.
How would you get an hour and 20 minutes? What work would you do to get?
Well, there's the 1 for the 1 hour.
Yeah.
And then 1/3 would be 1/3 of 60 minutes. So 60 minutes divided by 3.
Okay.
There's the 20. Yeah. Okay, so here's what I want to do. I know we have one more problem, and there's no way that we're going to finish it in time, and that's fine. So this section of homework is going to take you a while. Did you get that sense when we were working through this? Okay, so here's what we'll do. Your homework from 1.1 is definitely due tomorrow, no question. My best suggestion and advice for you is to finish as much as you can of 1.2, but I'll push it off one more day to be due on Thursday instead. But if you try to do all of this on Wednesday night, along with what I cover tomorrow, that's not going to go well, right? Not going to go well. So please start 1.2, but we'll push off the due date for it till Thursday. Maxwell.
Do you want us to turn in our homework on Canvas? How do you decide?
You're not turning in anything. You're doing all your homework inside of my math lab. I would keep all your written work there so that you can support and you go look back, right? But you're not turning any of the homework in. Also keep in mind that list of homework problems that applies to your quiz. We're still planning on doing a quiz on Thursday. So I would start working on those list of problems as well so that you have them as a resource on Thursday.